All right, so welcome back. We went over hydrogen atom last Friday, and today we're gonna extend our discussion of hydrogen atom, go beyond the spherical s atomic orbitals. So today we'll be talking about the 3p and 3d atomic orbitals, and then we'll briefly go over the fourth quantum number, which is electron spin. So electron spin, that's a little bit abstract, so we'll look at it from the experimental perspective and see why we say there is a fourth quantum number, which is the electron spin. And at the very end, we'll touch a little bit on atomic orbitals on many electron problems. Okay. So before we get started, here is a quick review on what we discussed in our last lecture. So in our last lecture, remember we're talking about the solution for hydrogen atom for the solution for hydrogen atom is a three-dimensional problem. And because it is a three-dimensional problem, naturally we have three quantum numbers that's associated with the hydrogen atom Schrodinger equation solution. So in this case, the three quantum number we're using, the first one is a principal quantum number. So that's associated with energy. So for hydrogen atom, we have En equals to negative z squared over n squared. That's in Rydberg. So first principal quantum number that describes the energy levels. We also have the angular momentum quantum number, and note the selection rule here, right? So the angular momentum quantum number, the maximum number can only be n minus 1. And this is why we have 3p orbital, 1 s orbital, 5d orbital, etc. We also have our magnetic quantum number. Again, we have the selection rule here. It can only take the value from negative L plus 1, all the way to positive L. All right. And then we went over the actual solved s orbitals. So again, because we're talking about hydrogen atom, has only one electron, so the wave function of the hydrogen atom can be solved exactly. So in this case, when we're talking about atomic orbital, it is equivalent to say that's the wave function we saw. All right, so the wave function and the atomic orbital, these two terms are equivalent for hydrogen atoms. So on the left-hand side, this is the solved wave function and a general picture of what it looks like. And note that in the solved wave function, we have a node in the wave function. So that's the 2s. For the 1s, we don't have any radial node. So what does a node mean? A node means that at this position, the wave function is changing its sign, right? So before it's a positive number, after the node, it's a negative number. So the wave function changes its sign at that radial node. What's the physical meaning of a node? So the physical meaning here is if we take the wave function and do a square of that wave function, what we're getting is at the radial node, at the node where your wave function is 0, around this position, there is low probability of finding the electrons. So if we plot that wave function, take that absolute value squared, by definition, we got the probability density function of finding that electron somewhere in space. All right, so the result of this radial node at around 2 Bohr radii is that you have low probability of finding the electron. So this is the real electron contour plot, which the brighter the color is means the more likely you find that electron in that region. So what we have in this part, that's where our radial node is. All right, so for the 2s atomic orbital, you have high probability in finding the electron within that small circle, where r is smaller than 2a naught, and also outside, right, when it's bigger than 2a naught. But around that radial node, you have very low probability of finding the electron there. So that's the physical meaning of a radial node. Because your wave function is 0, that means you have low probability of finding the electron around the node. All right, so this part is just a quick review on what we talked about in our last lecture. Do we have any questions before we move on to p and d orbitals? Okay. So now we're ready to move on above the s atomic orbitals. So here, because it's above the s atomic orbitals, let's start from the p atomic orbitals. So when we're saying it is a p atomic orbital, what we're meaning is its angular momentum quantum number L equals to 1. So that's the L equals to 1 term. That's just the other way of saying this is a p atomic orbital. Your quantum number, your angular momentum quantum number L equals to 1. All right, and for L equals to 1, we went over this last lecture as well. Your magnetic quantum number M can take 3 allowed value. So that's -1, that's negative L, and then L plus 1 and L minus 1, that's the same. So in this case, that's -1, 0, and 1. So the result of M can take 3 different values is we have 3 different p orbitals. So this we also went over last Friday. What it means when 3 different orbitals is 3 atomic orbitals. That's equivalent of saying we have 3 different p wave functions, right? So we will have p 2, 1, -1, 2, 1, 0, 2, 1, 1. So that's where we got the idea of there exists 3 p orbitals, because you have 3 magnetic quantum number. All right, so what does the wave function looks like? We always start from the actual mathematical function here. So again, we'll take it to, let's look at the mathematical representation first, and then we'll look at the graphical representation. So like the s orbital, all your wave function will have a radial part and the angular part. So for the p atomic orbital, the radial part is showing here. Let me just highlight it. And then the angular part is on the right. So if we look a little bit closer, all right, so this mathematical function looks very complicated, but what I want you to know is, can you tell me how many nodes are there in these 2 parts? So you don't need to go too deep in the mathematical representation, but I do hope you can tell me whether or not there exists a node. So if we look at the radial part, in this case, what we have, except when sigma equals to 0, we don't really have any radial node. There is no point where your wave function is changing phase. This is just an exponential that's going down. It doesn't have any radial node. However, for the angular part, we have a cosine function, and we have 1 node. And let's say my sigma is by definition 0 to 180 degrees. All right, so what I want you to do is, if I gave you a wave function, it might look complicated, but can you work out how many nodes are there by just looking at the wave function? All right, so what does our p orbital looks like? I'm not going to ask you to plot it in class, but you can try it if your math is good enough. Plug it into like MATLAB or Python, ask the program to plot it out for you. And what you should expect is somewhat like a dumbbell shape. You probably already see this somewhere else. But this is actually, like, if you plot out the mathematical function listed above, that's how you get the dumbbell shape. And this is my pz atomic orbital. It aligns along my z-axis here. That's one of our p orbitals. And by drawing it, by drawing the shading, we know that angular node plane is the XY plane. All right, so before we move on, to emphasize again, when we're saying there exists an angular node, means that when the wave function passes through that angular node plane, it's going to change phase. When I say change phase, means like your wave function is switching from a positive number to a negative number or vice versa. And if we look at the probability, what it means is there exists a low probability region. Right, so what it means is in between those two dumbbells, around that angular node plane, you have a low probability to find that electron in space here. Okay. And the other way to use the solved wave function for the p atomic orbitals, now we don't have a spherical shape, so I don't expect you to work on the radial probability or so on, because the math becomes a bit too complicated. But you might be asked to solve for the average distance using the same mathematical equation we had before. So in this equation, we have the L term, which is our angular quantum number. And we can quickly work on this together. So for a 2p orbital, so note that in here we have the NL, right? So for this one, N equals to 2, L equals to 1. So that's where this 2p comes from. We write it out. N equals to 2. For hydrogen, Z equals to 1. 1 plus 1/2, 1 minus 2 squared. On the top, we have 1 times 1 plus 1. You can do that calculation. That gives you around 5 A0. So that's saying what's the average distance of finding a 2p electron for a hydrogen atom. All right, so that's a 2pz that aligns along the z-axis. We have 2 more p atomic orbitals you should expect, right? Remember we were talking about, we have 3 possibilities here, and pz aligns along the z-axis. So naturally, we also have px and py that aligns along the x and y-axis. I'm just going to draw it with you here, and when we're doing it, just you can also think about how do you label the angular node plane. So for example, the 2px, we have the px aligns along the x-axis. And here we can have the angular node plane at the yz plane. And likewise, we can do so for the py atomic orbital. It's going to have the similar dumbbell shape. And my angular node plane is my xz plane. All right, and a little bit of the extra here before we move on. So remember we were talking about the 2pz atomic orbital. We were saying that's equivalent to say the wave function is 210. But for my x and y, these are not actually 211 and 21 negative 1. So these are just, they are actually like linear combination of the 211 and 21 negative 1. So these are extra. What I want to say is I don't expect you to know how to assign your magnetic quantum number to the atomic orbitals for the p and d atomic orbitals. You only need to know that 210 corresponds to the 2pz, and that's all. All right, so before we move on to the d atomic orbital, I want to go over the 3p atomic orbital, where in this case, you have both radial and angular nodes. So again, we start from the wave function. It looks very complicated, but here's what I expect you to know. Let's look at the wave function together. We have a bunch of the constant term here. So on the left-hand side, this is my radial part. And by just looking at these equations, where sigma is basically just your radii, atomic radii. So what we have find here is we have the 6 sigma minus sigma squared term. So what it means is that when your 6 sigma minus sigma squared equals to 0, or when your sigma equals to 6, you have a radial node. All right, so this is what I want you to get from these complicated mathematical equations. Can you tell me how many nodes are there? Can you tell me the position of your radial node by just looking at the wave function itself? So yes?
When it says EXP, is that exponent like meaning?
Yeah, that's just exponential. So EXP just means exponential term here. And on the right-hand side, we have our angular part. And again, this is a cosine term, so for theta within 0 to 180 degrees, we have one node. So in total, look at it. We have the n equals to 3, and total node equals to 2. So here is one of the very important rules we briefly mentioned last lecture, but I want to emphasize again. It's a total number of nodes in your atomic orbital always equals to n minus 1. All right, so the total number of nodes, that's taking consideration of both angular and radial nodes. So total number of nodes always equal to n minus 1. So for n equals to 3, we have a total of 2 nodes. And before when we were talking about 2p or 2s atomic orbital, but n equals to 2, the total number of nodes equals to 1. And for 1s, n equals to 1, so there exists no nodes in your atomic orbitals. So that's also a nice sanity check when you're deriving the number of nodes here. Yes? Sorry, I can't hear you. Yes, so for the question is, well, how do we solve for the radial nodes? So here, remember the definition of node is when your wave function equals to 0 and the change is sign. So the way to solve it is to find where your sigma equals to 0, depending on where your theta is. Sorry, where your wave function equals to 0, depending on where your sigma is. Sorry, not very good at with these correct nomenclatures. Okay, so moving on to the shape of the 3p atomic orbitals. So let's look at 3pz. Again, it's a pz atomic orbital. So what it says is my pz term is going to align along the z-axis. This is just my way to do it, but you can do it your own way. But I think the best way to do it on my end is to write out where the node plane is. So first thing first, we know that node plane aligns along the xy plane. All right, so this is my angular node plane. That's xy. We also have the radial node, where I'm going to use a green color. This is something we solved. When sigma equals to 6. And remember, sigma equals to ZR over A naught. So you can also solve for it. And then we can draw our dumbbell shape. So it's aligned along the z-axis. So I'm just going to draw my part in and out my node. And then I shade it accordingly, right? So whenever there exists a node, I change my shading. So shade, no shade, and this one is shaded. Again, so the way you see it, the way you draw these atomic orbitals with angular and radial node is you draw the node plan first, and then you draw your shape of your atomic orbitals. Then you shade it based on the position of your node plans. So here is the drawing of the atomic orbital, and we also have the contour plot. So what we have here, again, it's the same idea. In the middle, we have our angular node plan. And then we have our radial node at a given radii. And this is probability contour, so we don't have shading. Okay, and let's do one more example together in how to draw your atomic orbitals. So the question here is to sketch the atomic orbital and the probability density of the wave function 5410. So 410 here, or I can just ask you to draw it for the 4pz. All right, so 4pz and this 410 are equivalent. They're just the quantum number of the 4pz atomic orbitals. All right, so we're sketching the 4pz together. And this is the typical way I would approach the problem. So let's start by writing out the quantum number. So we have n equals to 4, that's a principal quantum number, L equals to 1, and m equals to 0. So from looking at the quantum number, what we can get is first the total number of nodes equals to n minus 1, which is 3. All right, so total number of nodes, that includes both angular node and radial node. So for L equals to 1, my angular node equals to 1. So as a result, my radial node equals to 3 minus 1 equals to 2. So that's how I work out the number of angular and radial nodes. So total number of nodes equals to n minus 1. That's from the principal quantum number. The angular node comes from your angular quantum number. So L equals to 1, you have 1 angular node. L equals to 2, you have 2 angular nodes. We'll see the d orbital very soon. And then with these two numbers, you can solve for the radial node. That's just basically 3 minus 1 equals to 2. Don't really need a calculator to do it. And then we can do the sketching together. So I always start by drawing the Cartesian coordinates. And in this case, what we're having, so let's draw the angular node first. So we have 1 angular node and 2 radial nodes. So for this question, we don't know the position of the radial node, but you can well imagine if I gave you a wave number, a wave equation that you can solve for the radial node, I could also ask you to label where that radial node is. But for this problem, I'm just sketching 2 radial nodes here. And then we draw our atomic orbitals accordingly, inside out, these node planes. And then we add the shade in. So whenever there is a node plane, it changes the shading. So shaded, not shaded. Shaded, not shaded. And also on the top. All right. So the green ones are my radial nodes. And this is my 4pz atomic orbital. all right? Yes?
How do you know which ones to shade?
It doesn't matter. So this is one way to shade it. As long as you alter the shading at the node plan, I don't care if it's shaded this way, or you could also like change it to this way. So as long as you alter your shading at the node plan, you're correct. All right, there are two different ways to draw it. Yes?
How do you tell whether it's like PZ or PX or PY?
If it's PZ, it aligns along the z-axis. If it's PX, it's aligning along the x-axis, and PY aligns along the y-axis. In the question, I'm given 410. So whenever you see the magnetic quantum number equals to 0, that's likely to be your z atomic orbitals. I'm not going to ask you to distinguish x and y from the quantum number. So I will tell you if it's x or y orbitals you should be drawing.
And if you don't mention it, it's just going to be Z?
If your m equals to 0, that's going to be z. Yes?
How do you tell if it's X or Y?
I'll tell you if it's x or y, yes. All right. The question also asks you to sketch the probability density. So know that atomic orbital and probability are two different drawings. So your atomic orbital, that's your phi 410. The probability density, that's your phi 410, absolute value squared. So the difference here is your probability density functional doesn't have any shading. It's all going to be positive. But you'll still have these node plans. So let's look at it together here. So I put a real thing on the right, but we can draw it the same. We have the angular node in the middle. And then we have two circles representing the radial nodes. And then we draw our dumbbells alongside with each other. Right, so it's the same idea. Here we have likewise, we have two radial nodes and one angular node. Again, the physical meaning of these node plans are just the low electron density region in your probability density functional. What it means is around the node, you have low probability in finding the electron there, in finding your 4pz electron there. All right, so before we conclude, for these types of questions, again, for any atomic orbital, n-1 gives you the total number of nodes. That includes both radial node and angular nodes. And your angular momentum quantum number L will give you the number of angular nodes. All right, so any questions before we move on to d-atomic orbitals? Yes?
Do each of the inner circles correspond to an n number?
So the question is, these inner circles, what's the physical meaning of these inner circles? You mean the dumbbell part or the green one?
The dumbbell.
Okay, so these dumbbells, they're not independent inner circles. They're part of your wave function that have different shades. So what we have is everything in blue here, they're just one wave function. The different shading just tells you whether it's positive or negative. So whenever your wave function reaches a node, whether it's angular node or radial node, it changes its phase. Means it's switching from negative to positive or positive to negative. All right, yes?
Did you purposely not shade in the dumbbells on the probability density contour?
Right, so I didn't shade on the probability density contour because they're all gonna be the same positive number. It's a probability, right? It must be a positive number. So you can not shade everything or shade everything, but there doesn't exist anything, your switch shading in your probability density functionals. All right, now we're moving on to talk about our d-atomic orbitals. So these wave functions will become a bit too complicated. So for the d-atomic orbitals, I'm no longer showing you the actual mathematic functional. But again, in this case, look at, the way to look at those mathematical functions is trying to find an idea about how many nodes are there given the wave function. But for the diatomic orbitals, we're pretty much focusing on the shape of these atomic orbitals. So for diatomic orbitals, that's equivalent to say your angular momentum quantum number L equals to 2. And for L equals to 2, your magnetic quantum number can take 5 different values, right? Plus minus 2, plus minus 1, and 0. So this is why you have 5 different d atomic orbitals. So your L equals to 2 tells you that's a d atomic orbital. That the magnetic quantum number m pretty much tells you the orientation of your d atomic orbitals. So I'm just going to write it out here, but you don't really need to know which corresponds to which for the d atomic orbitals. So we have 3, 2, negative 2, that's my dxy. 3, 2, negative 1, that's my dyz. 3, 2, 0, that's dz squared. 3, 2, 1, that's dxz. 3, 2, 2, that's dx squared minus y squared. So, I mean, you don't need to know how these m corresponds to the orientation, but I'm just going to put it here as a little bit of the extra. And what I do want you to know is for 3D atomic orbitals, right? We have n equals to 3 and L equals to 2. So this n equals to 3 tells you the total node equals to n minus 1, which is 2. And L equals to 2 tells you number of angular nodes equals to 2. So for the 3D atomic orbitals, we have no radial nodes. All right, so that's how we get the idea about why we don't have any radial node for the 3D atomic orbitals. They're just information buried in your quantum number combination there. Okay, and now let's look at the shapes of our d atomic orbitals. So I'll spend some time just draw it with you. And these are the drawing of these atomic orbitals you should get familiar with, especially in the future of your chemistry classes. So start from the 3D xy. It means the 3D xy locates on my xy plane. And my angular nodes are my xz and yz. So if we draw it out, it locates on my xy plane. And my xz and yz are my angular nodes. All right, so if I shade this part, there's a node here. This one is not shaded. This one shaded. This one not shaded. So logic is the same. Whenever you see there is a node plane, you switch the face. You switch the shading of your atomic orbital drawing. So that's the dxy. dyz, I'm going to take the more lazy way to draw it because I'm just changing the axis label here. Y, Z, and my angular nodes are my xz and yz. Xy and xz. All right. And then the next one, the DZ square, this one is a little bit odd because it doesn't have your normal shape you expect. So in this one, we have the maximum amplitude along the axis, and you sort of have a donut on the XY plane. So if you draw it out, say this is my z-axis, and here's my x and y-axis. The way we normally draw it is something like this, with a donut. It doesn't look very counterintuitive. The other way to think about it is if you look from top down with that little eye, and we look at my x and y. And what it looks like is like this. So it's not connected, so it's different from your XY, the XY atomic orbital. And these are my radial nodes. So it's something like this. This one is a little bit odd. I posted a link on your Canvas site, so you can go click that link and actually play around with those atomic orbitals, rotated in three-dimensional, and get an idea about what these atomic orbital looks like in three-dimensional. Okay, and before we move on, we have two more atomic orbitals to draw. We have the XZ. So my XY and YZ are my node planes. And we can shade it accordingly. And at the very end, we have our dx squared minus y squared. So this one is again on the x and y plane. The only difference is now, instead of having it in the empty area, it actually aligns along the axis. And the angular nodes go diagonal here. All right. And again, like, try not to remember every drawing. The best way to do it is remember where the angular node plane are, and then draw your orbitals accordingly. So this is the end of our d atomic orbitals. We have any questions? Okay.
Okay, I have one question.
Yeah, sure.
I think it was on the last orbital you drew.
Mm-hmm.
This one, the one before it. Actually, no, sorry, this is the donut. I was just a bit confused on the side view you drew.
Right, so this one, you can just click that link on Canvas and actually see that three-dimensional atomic orbitals of the dz square and try to rotate that three-dimensional orbital and look at it from down up. So it doesn't look very obvious from what we have here. Okay. All right, so we talked about the three quantum numbers that defines the shape and orientation of your atomic orbitals. And now we want to briefly touch on the fourth quantum number, which is electron spin. So the actual background of electron spin is a bit too complicated, but I just want to introduce you with electron spin using an experiment, which is the Stern-Gerlach experiment. So in this experiment, the setup here is, say we start from a beam of ground state hydrogen atoms. What it means is our ground state hydrogen atom, when we say ground state, they should all have the wave function of 5100, right? So when we say that's ground state, that's 1s, means all our electrons in that original beam should all have the same quantum number combination. It all have the same wave function. So naturally, we expect these electrons in hydrogen atom to behave the same. Right, so this is where our expected spot comes from. But as you probably already see, what we have here is when this beam of ground state hydrogen atom passes through this non-uniform magnetic field, scientists observe two different spots on the receiving plate. So what it means is although your hydrogen atom that we start with all have the same ground state, which is 100, we still have two different types of electron in these atomic hydrogen atoms. So that's why we need a fourth quantum number to distinguish these two different types of electron, even if they are all in the 1s atomic orbital. So what we mean is, like, start here, right? All hydrogen atoms are in the initial beam, are in identical ground state. But we also still observe two different separate spots on the receiving panel. So what it means is the non-uniform magnetic field distinguish two different types of electrons. So that's why we need a fourth quantum number, which is electron spin. So the physical meaning of electron spin is it describes the orientation of the magnetic moment of the electron. If it doesn't make sense to you, what it means is how electron reacts with external magnetic fields. So in this case, your electron spin can take two different values. For hydrogen atom, it can either be 1/2, or what we call it a spin up, or it can equals to -1/2, or spin down. We'll talk about that when we're talking about NMR spectroscopy at the end of the quarter, but the fourth quantum number are electron spin. And this is why every atomic orbital we have can take up to two different electrons, one spin up, one spin down. All right, so far we've finished everything talking about the hydrogen atom. So this is the most simple scenario you can imagine. That is a real system. You have one nuclei, you have one electron circulating it. Well, not circulating it, but one nuclei and one electron. And here we have the quantum mechanical picture of the hydrogen atom. So several information here. This is a quick summary. When we're talking about atomic orbital, it is equivalent to a wave function, phi, n, l, and m. All right, so this means n and l and m, the combination of these three quantum number gives you a specific quantum state. The atomic orbital is equivalent to hydrogen wave function. So when we say hydrogenic wave function, means it's atoms that has only one electron. So helium plus is also a hydrogenic wave function. And for all electrons, we have four quantum numbers to describe them. We have our principal quantum number n that tells you the quantized energy levels. So this part just Rydberg. And we have the z squared over n squared. So the total number of nodes in your it's given by your principal quantum number n. The total number of nodes, including both radial and angular, equals to n minus 1. Allowed value for your principal quantum number is all positive integers from 1 to 3 and so on. We also have our angular momentum quantum number L that gives you the quantized square of angular momentum. The number of angular nodes equals to your angular momentum quantum number L. And the allowed value of L starts from 0 to all the way to n minus 1. So you don't have any 1p atomic orbital because you don't have any, your L count equals to 1 when your n equals to 1. And conventionally, we have different names for these L atomic orbitals. When L equals to different value, we have different atomic orbitals. For L equals to 0, we have S atomic orbitals. I'm just going to quickly draw it here, but feel free to practice here as well. So we have the S atomic orbitals, that's spherical, when L equals to 0. For L equals to 1, we have P atomic orbitals that has 1 angular node. All right, so we have this dumbbell shape along X, Y, and Z atomic orbitals. And for L equals to 2, we have D atomic orbitals with 2 angular nodes. And we just did the drawing together, so I'm just going to quickly draw it here. So the dz square is our dumbbell shape. The xz aligns along the x and z plane, and we have the angular nodes on the xy and zy. Likewise, xy, yz, and then the x squared minus y squared. You need to know how to draw these angular nodes in your d atomic orbitals. All right, take-home message when you're drawing these atomic orbitals, whenever you have a node, you change the face of your atomic orbital, you change the shading of your drawing. And then for the magnetic quantum number, this tells you the orientation of your atomic orbitals. And I don't really expect you to know how to correlate your magnetic quantum number to the actual name or orientation of those atomic orbitals. And then at the very end, we have the electron spin. We'll save the multi-electron problem to next lecture. But here are all my stuff for your hydrogen atom. All right, thank you very much.